In this video, we are going to learn about the multi-class segmentation using the UNET architecture in the TensorFlow framework. Here we are going to use the human parsing dataset which contain 20 classes. Hello friends, welcome to this video. I am Nikhil Tomar and you are watching Idiot Developer. Make sure to subscribe the channel for more such videos. So now we're going to begin with our tutorial. So first of all, let's have a look at the dataset. So the name of the dataset is CHIP, which refers to Crowded Instance Level Human Parsing Dataset. The link of the dataset is in the description. Now I will show you how the folders and files look inside the dataset. So here we have three folders: testing, training, and validation. We have a mat.mat file which contain the color scheme, basically which RGB code refers to which class. As it contains 20 classes, so we're gonna have 20 different RGB code. So first of all, let's have a look at the readme. So here if we see, first we have images name, which would in images, then so these are the folders name. You see inside any of them. Let's go to training. So if you see images folder we have here, then we have categories ID. So this is basically the description of each folder. So here we are working with multi-class. So first of all, we need images. So the images folder we're going to use. Then we need the RGB mask, which would be in the categories. That is visualize semantic parts segmentation. It also has the instance level, but we don't need instance level. Okay. And the order of semantic parts segmentation. So these are the 19 classes, and first or the 0th class is the background. So this is 19 plus 1. So whenever someone say in multi-class 20 classes, so it means 19 would be main classes and 1 would be background. Background is also a class. Same is the case with binary segmentation, where we have two classes, a foreground class and a background class. So foreground is the main, so there we only consider it as one class. But here we have 19 plus 1 class, that is 20 classes. So now let's take a look at the samples of the images. So it's a huge data set. I believe it has more than 28,000 images. So I'm not going to use all the images because it is very difficult to train and it is very time consuming. So this is first image sample. You see it contains wide variety of human images of different size and resolution. You see their height and width shown here. Now let's see the mask. So our masks are in categories. So let's take a look at them first. And these would be in RGB. They are not in grayscale like we have in binary segmentation. When you move from binary segmentation to multi-class, the mask would be different. So automatically their processing would be different. In case of binary segmentation, it is really simple. We just divide the whole image with 255. That would convert the whole image into 0 and 1. So it would have two classes, 0 and 1. And here we have RGB code. So we also need to convert them into proper classes. So here the pixel values would be, because we have 20 classes, so they would be 0 to 19 like this. So we need to normalize these RGB masks. So each RGB code here indicate a different class. So if we see, the face is in blue. Okay. So these are some of the mask sample. Now each of these folder also contain other things. And if I show you category IDs, let's say for once, I believe it would contain the instance sample. So we need to wait because this is really okay. These are normalized masks. So normalized masks are basically where it is a grayscale image and it would contain the pixel values in the range of 0 to 20. Okay, 0 to 19. They would be normalized. So let's say background is in 0. So all the pixels for the background would be 0, 0, 0. Let's say for face it is 1. Then for the face all the pixels would be 1. Okay. So we're going to learn how to normalize those RGB masks into these grayscale masks. We're also going to learn that, because that is an essential part of multi-class segmentation, because sometimes you may not get the normalized mask, but mostly what you will get are these RGB masks. So this is really essential part. Okay, I just want to make sure that you focus on this part. When I'll write the code, just focus on that part where we convert these RGB masks into normalized grayscale mask. Okay, because people mostly question when you watch my binary segmentation videos, most of you comment out that how do we use it for multi-class. So today you're gonna learn how to do multi-class segmentation. Okay, so first of all, let's move on to the architecture part, because here we're going to use a simple UNET architecture, because UNET is one of the most starting point for any segmentation task. So we're going to begin with UNET architecture. So here we have imported all the layers which we require for the implementation of UNET architecture. And in the next line, we have imported the model class, which would take the input and output of the architecture and give us a model. Now next, we are going to implement the convolution block. Let's write the name of the function con block. It would take two inputs or arguments. First would be the inputs, that is the previous feature map or the input feature map. The number of filters, that is number of output feature channels. So number of filter basically indicate what would be the output feature channels of the convolution layer basically. Okay, so now let's define some layer or write the layers part. So first it would have a 3 by 3 convolution layer. So we're going to say con 2D. First would be number of filters, that is num underscore filter. Then it would have the kernel size, so it would be 3 by 3. So we're going to say 3 here. So it would automatically assume it is 3 by 3, that is a square matrix. Then we're going to write padding, that would be same. So padding equal to same means that the output feature map would also have same size as the input if stride is equals to 1. So by default stride would be 1, so we don't make any change in stride. Now we're going to give the input to this convolution layer, and x would be the output feature map of this convolution layer. Next it would be followed by batch normalization. It would take the output of convolution layer. After batch normalization we have the activation function, and here we use ReLU activation, and the input to this ReLU activation would be output of this batch normalization. So initially when the UNET paper was out, the batch normalization was not there, but over the time people started using it, so I'm also adopting it. But it's up to you that whether you want to use it or not. I believe that it gives you performance boost, and also helps in the easy of the training, it also fast the training. Okay, that's why I'm using it here. Okay, so let's go back to the con block. So we have 3 layers here. First is convolution, batch normalization, and activation. So now we need to repeat same set of layers again. So I'm going to copy it and change the input. So now we're going to get the value back, that is this. Okay, the x, the output of this second ReLU activation. So we are done with our in the convolution block. Now we're going to move on to the encoder block. First again would be the inputs, that is the input feature map. Second would be number of filters. So the encoder block begin with the conv block. Conv block is going to take the inputs and the num filter. So now we have the output of conv block, and this output would go into a max pooling layer, that is a 2 by 2 max pooling. So 2 by 2 max pooling means, let's say the height and width of the input feature map, that is the x here, let's assume is 128 by 128. Then with 2 by 2 max pooling, the output feature map of this max pool 2D layer would be 64 by 64. So it basically halves the height and width, because we say 2 by 2, so it halves them by factor of 2. So now this function encoder block gives two things. First is the output of cone block and second output of pulling block. So why two? The simple reason here is that UNET uses skip connection. So the output of this cone block would act as skip connection also, and this P would act as input to the next layer. So now let's begin by building our unit. Let's say build unit. First it would take input shape, and now one more variable, that is number of classes. In case of binary segmentation we only have one class, so we don't take class number of classes. Okay, but here we take, because number of classes can change in multi-class segmentation. So inside build unit function we're going to define the input layer. Then this input layer would take the input shape. So we have our input layer. Now we're gonna start with the encoder block. See, we're gonna call our encoder block here. We're gonna give it the input, that is inputs layer. Number of filter would begin with 64. Now it's gonna give two features at output. First is skip connection, so we're gonna call it S1. S1 refers to first encoder block. Then P1, that is output of pulling block, but first encoder block. Okay, so like this we're going to continue with our second encoder block. The input would be P1 and number of feature would be 128, that is double of 64, that is 64 into 2 is 128. So like this we're going to have two more encoder block. Input would be P2 and number of features 256. Then S4 comma P4 encoder block, input P3 and number of filters 512. Now it completes your encoder block. Okay, then in between encoder and decoder there's a bridge for a simple cone block, so we will call it B1 cone block, and input would be P4. Number of filters, that is 512 into 2, that is 1024. So this is our encoder and basically the bridge part. So now let's run this and check if it works or there is any error, because error or a part of programming, when you write some code, error would always be there. If there's no error, this means either you are genius or you don't do anything, just simply copy paste. Because when you try to do something you will always get an error. Okay, so let's have an input shape. So let's say for now 256 by 256 by 3rd. Then we're gonna call our build unit. So we're gonna have the input shape. Okay, we also require num classes. So let's say for now let's give it 20, because we have 20 classes. Let's now print the shape of B1. Okay, it's unit.py. Okay, here you can see a lot of messages from TensorFlow and other thing. And at last, if you see the shape of the feature map, that is 16 by 16 by 1024. So this feature map would be input to our decoder block. So let's now move on to the decoder block. So in encoder block, we extract the features from the input image, and in decoder block, we try to upsample those features and try to synthesize a segmentation mask at the end. Okay, so this decoder basically learns how the feature maps, which would help us in generating the fine quality segmentation. But in case of binary, it would be easy to have a good fine quality segmentation mask, because it has only one class. But in multi-class, especially here in this example, in this video, we have 20 classes where 19 are main classes, one is background. So they would be the segmentation quality would not be that good. Okay, because there are 20 different classes, so model have to force itself to learn 20 different representation for each class and give you a better quality mask. So the problem basically occurs when two classes are joined, so their edges would always be problem. Okay, so let's continue with the decoder block. The decoder block would take two inputs. First would be your previous feature map that we represent with input. Second would be skip connection. and third number of filters. So first of all, it is followed by a trans transpose convolution layer. So that is con 2D transpose. It take number of filters, kernel size would be 2 by 2. So we also gonna write it like this, and strides here is 2. Okay. So strides 2 basically means we want to upsample the feature map by factor of 2. Okay. So let's say your input feature map, that is this inputs. Let's give this input to this layer. Let's say the size of this inputs is, here it is 16 by 16 if you see. So when it passes through this layer, this transpose convolution, it would become 32 by 32. Okay, so let's check this out for now. I'll show you. Let's print the size of x dot shape. We're gonna call decoder block here, and because for now it only take the previous feature map, that is b1. Save and run this. Okay, it also take num filters. That's my mistake. Let's give num filters here, and let's give num filters here. So number filter would be half of 1024. So in the encoder part, we increases the number of filters and decreases the height and width. In decoder part, we decreases the number of filter and increases the height and width. So let's run this code again. So you can see this time the height and width increases from 16 by 16 to 32 by 32. So we are done with the transpose convolution part. So after transpose convolution, we gonna concatenate the output of this transpose convolution with skip connection. So because the height and width of this feature map is 32 by 32, so we need a skip connection with exactly same height and width. So what we gonna do here? I'm gonna print the shape of all skip connection from S1 to S4. Oh, spelling mistake. That is when you're typing very fast and some keys misses. Okay. So here you can see the feature map begin, not the feature map, the skip connection has a height and width. The first, that is of original input. So our input feature map, input image, not feature map. Input image have a size of 256 by 256. So first skip connection would have that size. Second would be half of that. Then again half. Then again half. The last one would have 32 by 32. So this means S4 can be used as a skip connection for the first decoder block, and likewise then S3rd, S2nd, and S1st. Okay, so let's continue with this. We're gonna say skip here. You can give any name. So x equals to concatenate, concatenation layer. First would be x, then skip. We are done here. Now after that we have a convolution layer in the decoder at the end. So because both encoder and decoder we have this convolution block, so we simply write a function instead of writing those 6 layers again and again. So it would short and make us more productive. Then it would take number of filters. We're gonna give this x back. So in decoder we don't have two outputs say like this. That is, we only have that in encoder, not decoder. So we are done with the decoder. We're gonna give output as t1. So let's print its shape and check whether we have any error, any issue, or any problem. Okay, so it's working fine. Now let's have more decoder block. So second will be d2, decoder block, input will be d1 as third, then again half of 512, that is 256. So what I'm going to do, I'm going to copy this, again paste it. That is more productive. Instead of writing input will be d2, skip connection s2, number of filter 128. Then last decoder block, that is d4, input would be d3rd, skip connection s1, number of filters 64. So we are done with the decoder block. So let's print the shape of d4. So the height and width of d4 should be 256 by 256, and number of filters should be 64. So let's save and check it. You can see height and width 256 by 256. That is really important. and number of filter 664. Now we need an output layer, so we're going to call it outputs. That would be a simple one by one convolution layer. So here number of filter would be equal to number of classes, so each filter would represent one class. Then kernel size would be 1, padding equals to same. Then we have an activation function. Activation, oh, this a should be small. Activation would be softmax. So that is one main difference. In binary segmentation, we use sigmoid activation function. In case of multi-class, we use softmax activation function. So let's give the input to this layer, that is D4. So we now have both the input and the output. Now let's call our model function. First would be inputs, then output, then we're gonna get this model back. Okay, so we are done with the implementation part. I hope you are not new to the UNET segment architecture implementation. I have a lot of videos on UNET. You can watch those. Now we're going to say model.summary. And if you are new to the UNET implementation, I hope this video make it really easy for you to understand how it works. Okay, so you can see summary of the UNET architecture. Let's go to the starting. Okay. Here you can see the initial input layer is 256 by 256 by 3rd. Then if we go move back down, a lot of layer, and if we go to the last, that is the output layer, is 256 by 256 by 20. So 20 refers to our number of classes, so you can change it accordingly. So we are done with the UNET implementation part. Now we can move on to the training part. The training is basically, I think, new for most of you because this is multi-class segmentation. So there would be few major changes I would highlight and just focus more on that part. Okay, because binary is really simple. In multi-class there would be few changes. So I would make sure that it would be easy for you to transition from binary segmentation to multi-class. If you have the existing binary segmentation, you want to use it for multi-class. So how are we going to do that? First of all, let's import all the files and the functions and every other thing we require. First we have this OS library, then we have this variable set to 2. So this we set it to 2 because we don't want those unknown messages, kind of warnings and or all those things. We don't want these information. We just want our required thing. So this would not come in this training part because of this line. Then next we have numpy because we are dealing with images, and when we read images using OpenCV, we read them as numpy. Then we have pandas. I think we don't require that, but let's see that at the end. Then we have globe. So to get all the files path, that is images path and mask path, we're going to use globe. Then we have scipy. We're going to use it at some place, I'll tell you. Then we have train test split because in this video we're going to use the training data set. Okay, the training part. If you see the data set, it has training, validation and testing, but we're going to use the training and split it into training, validation and testing. So that is why we need this and train test split. Then we have imported TensorFlow. That is our main framework in which we are implementing the complete multi-class segmentation thing. After that, we have some callbacks from TensorFlow. That is model checkpoint, reduce LR on plateau, early stopping and CSV logo. So I'll explain them when the time comes. And at last, if we have imported the UNET from the imported build UNET function from the UNET which we have implemented now. Okay, so first of all, let's define some global parameter. So this basically means that they can be called by any class, any function. So that is why we have defined them here with the keyword global. So first is image height, then image width. Third one is number of classes. The next would be classes. It would have like the class that is face, this and that, face here, etc, etc. That is the label, the text part. And the last is the color map. Color map would have the RGB code. Okay, sequentially. So they see both the classes that is the textual name, and the RGB code would be sequentially. So let's say the class 0 is background. So in the classes, we're going to write text as the background, and in column map, we have the respective RGB code. Okay, next we're going to define a simple function which is going to help us to create a directory. So this name of the function is create dir. It would take this path. So first of all, we check with this function, that is os.path.exist. If not, if this path does not exist, then make this path using the make dirs function. So that is really simple. Now let's move on to the main part. If name equals to main, this is our main function from where the execution of this function starts. So if we don't write this function, it would begin execution from the starting. So it is better to write this statement and write the code from here, so you know from where the execution will start. So first of all, we're going to seed the environment. We're going to call seeding first np.random.seed. We just see to make sure that the randomness is same every time we train, and also for reproducibility, because the layers are randomly initialized, so the randomness can change. So we don't want that change every time, because that can affect the training. That is why we just try to seed the environment as much as possible. You can also see other thing or other you want to seed, but I think these two are enough for me. The next, we're going to create a empty directory which would help us to save files and other things. So we're going to say directory save files. Simple. We're going to call our function create dir and call files. So we're going to have a folder called files which would have all the things saved inside it, and these all things are basically model weight file, the csv logger file which would be created while training, and one more score files, I think. Okay, next let's set some hyperparameter. Okay, so first would be the image height. Like with checking all the images, I find a mean height and width which would suit for all the images. That is 320, that is the height, and the width is 416. Just I'll tell you one essential thing here. Okay, because in UNET, if you see, every time when you go, the feature map is the height and width of the feature map is half. Okay, so just make sure that this parameter is divisible by the factor of 2, because let's say this is 320, when you divide it by 2 it became 160, 160 divided by 2 it became 80, 80 divided by 2 it became 40. Okay, so these number perfectly match each other. Let's say you divide 5 by 2, it became 2, it won't be 2.5, because image size would be 2 or the feature map size would be 2, not 2.5. So during concatenation it would cause a problem, because during in the decoder block, in the this transpose convolution, when you have input feature map height and width by 2, it would become 4, and the skip connection would have 5, so they would have problem. So just make sure this number is divisible evenly. So just remember that thing, or if you are confused with that, just have a height and width of 2 raised to the power n, that is 128 by 128, 256 by 256, 512 by 512, or those numbers basically. Okay, so I hope you get my point here, what number we need to choose, otherwise you're gonna have error in this implementation. Okay, so next hyperparameter would be number of classes. Okay, so we are done. Then input shape, let's define the input shape. That would be image height, image width, and number of channels. Let's set some more hyperparameter. First would be batch size, that is 16. So because I'm having a RTX 3090 which have 24 GB VRAM, that is video RAM, and my GPU can support 16 batch size. Maybe your can support even higher, so you can set the batch size accordingly. So sometime what happen is when you set large batch size, so you would get an OOM error in the TensorFlow, that is out of memory error. So that error indicate that your batch size is huge, is large than the memory available. So try to decrease the batch size, that is you can set it to 8, 4, 2, 1, what suits your system. Next would be learning rate, that is 1e minus 4. This is basically 0.001. This is 1e minus 4. Next, number of epoch we want to train. See, here we can set 100 for now, but this is according, because we are going to use early stopping mechanism and a callback in the TensorFlow. So what would happen? We're gonna use early stopping to check if the model is not improving, the loss rate is not decreasing, so we're gonna stop the training. Either you can set it to what I mostly do most of my experiments, I set it to 500 and set call and this early stopping mechanism to 20, 30, 40, 50, so that it stop automatically. But for let's set it to 100, because the data set is really, first of all, it's really huge, so we cannot have like large number of epochs. Let's set 100. Next would be our dataset path. So this is our dataset path. Next we're gonna have two more paths. First would be model path and second would be the CSV path. Model path, where would our model file would be saved, that is inside the files folder. Next is CSV path, where would our CSV file, that is data.csv file, would be saved inside the files folder. Okay, now let's work on loading the dataset. Let's have a function called load dataset. It would take the dataset path. So let's go back to the top. Yeah, not that top. So we're gonna have this path. So first of all, we're gonna load the data and split it. So our split would be 0.2. So this 0.2 basically indicate that 20% of the data would be allocated to validation and another 20% would be allocated to testing. So we remains with 60% that would be used for training. So let's load the images first. I'll call it images. Oh, mistake, that would lead to an error. So first of all, let's define the path. First would be path. Okay, now I'll show you the, so we are inside, so we are here. Next we would define the training. So I'm going to copy paste it here. After training, because we are extracting images, so I'll show you the folder again. We have this images, so inside this folder we have all our images which we want. So we're going to say images, and after that we're going to say star. Star basically means give us the path of all the files which is inside them. So this is the path. And next we're going to have our globe function. We're going to give this path to our globe function. So globe would extract all the file path, then globe would give us a list and we're going to sort that list. So this is the way we're going to load our images and mask. First sorted, then globe, then there's after training our segmentation mask, that is RGB mask, are in categories folder, and after that also we're going to write star. So this way we extract all the images and masks. So now let's do one thing, let's print images, number of images. So let's have string here. So we're going to say length in the curly brackets of images. Let's just check how many images we have, and I'm assuming same number of masks would have. You can see we have 28,000 images, near about 28,280 images. So we are not going to use all. What we're going to do, I'm going to cap it to, you can cap it to 1000, but here I'm going to cap it to 10,000 because that is what I can train. So we have seen this. Let's also print one more thing, images 0. then mask 0. So we're going to print the path of the image and mask which are at the index position 0. Okay, you can see the complete path. Let's ignore this, just get to the name. You can see it is 0.6.jpg, then 0.0.0. So name is basically should be same, because they represent that this image have this respective mask, this mask have this respective image, so they both should be same, and the naming indicate that. Let's say if I don't sort it here, let's see what happens, because sorting would make them in a specific order. If you see, if you don't sort this list, you would get a different image and a different mask, so they won't be fit to each other. Okay, so that is why when you extract these images, just make sure you sorted that list, otherwise you not gonna have the image and mask and pair in proper pair. So we have loaded the images and mask. Next we're gonna split them. Okay. I'm gonna copy the code from here. What we have done, first of all, we have taken this train test split function. Okay, so here in this train test split function we have given the images, then we have this test size is equal to split size, then a random state 40, then same for the mask. So let's have the split size. So split size is basically the number of images, that would be 20%, that is 0.2% of this entire data. So this would be in integer, because number of images would be integer, they cannot be float. Split multiplied by the length of images, so that is the split size. So we have our training and validation. So this means our training now contain 80% of the data and validation contain 20%. We're going to do the same thing again. We're going to split that train x and train y again, and this time we would have 60% data allocated to the training and again 20% to the testing. So this way we have split our data set, complete data, into 3 different parts, that is training, validation and test. You can make it 1%, that would be 80 10 10, or you can do it more, or 0.15, that is I think 70%, and 15%. So this makes our data set split part. Now let's get back this data and continue with our code. So now we're going to print the size of each of these training and validation set, training, validation and test. So this is training, then we print the length of train x, then it did slash, then train y. Same we do for valid x, valid y, then test x, and let's run it. So here you can see we have uses 10,000 images. So out of 10,000, 6,000 are used for training, 2,000 are used for validation, and 2,000 are used for testing. So dataset part is run. Now comes one of the most important part for the multi-class segmentation. Just focus here. So we're gonna have the color map here. Process the color map. So for multi-class segmentation, you need one thing, that is the RGB code and the classes. Okay, that is one of the most essential thing. So here the RGB code are inside this mat file, that is human color map.mat, and the name of classes, if you see, are given in this readme file, this hat, hair, glove, this. So these 2 things it is essential to have, otherwise there would be more complications, you need to write more code. Okay, because in this we have these 2 things, so it is really good for us. So I'm going to write a function called get a color map, and it would take the dataset path. So we're going to write that function. Okay, f get color map, where is the path. So first of all we have the we're going to write the path to the mat file. So we're going to call it mat path, First would be the path, the dataset path. Then the name of the file is human. Let me just copy paste it. It would be easy, more product. Name is human underscore color map dot mat. Now we need to read that file. Color map equals to, and here we use the scipy, that is mat. Okay, this as underscore. Now let's print this variable, this color map, and run the code just to see content inside this file. Okay, so if we see, it's a JSON or dictionary kind of thing. So first is header, it has something which is encoded because of this B, I think, and platform, then version, and I think this is the color map. You can see array with these six arrays which have three values. These three values indicated whether they are RGB format or BGR format. So we're gonna extract this color map. Let's print this color map. If you see, we have this entire array. So let's find the length of this array first. Okay, so we're gonna say length function, length of this array. So length is 20. This means these are the RGB code for our 20 classes. And here if we see the first one, it is background, that is 0 0 0. So 0 0 0 would always indicate the background. But if you see, they are not in RGB format, they are like normalized range in between 0 to 1. So they are in the range of 0 and 1. So let's multiply them with 256. That is our number of pixels in an image. We have pixels from 0 to 255. Okay, so this total ups to 256. So when we multiply anything between the range of 0 and 1 to 250, it would automatically get to that range between 0 to 55. So let's do not here, color map into 2 6. Let's print that and see. Okay, you can see we get a nice range, and these are our floating point float values. So these pixel values should be integer. Let's also change that. These should be unsigned integer 8. Let's run that. Now you can see proper integer values. So these codes are in BGR format. Okay, first is blue, then green, then red, and we need to make them to RGB. So what are we gonna do? The simple thing I'm gonna do. Color map equals to, first would be a loop for C in color map. So this C would have this individual array. This here we have this C0, C1, C2. So 0, 1, 2 are the index position. So let's, so what are we gonna do? We're gonna say, okay, this is a bit complicated, I'll try to understand. Okay, so first is an empty list. First of all, from C we're gonna extract C2, then C1, then C0. I think you know also transpose that. If you use the numpy to transpose, that would also work. But let's do this way. This is, I believe, is much simple, and not simpler but it's easy to understand for me to do. From each of these array we extract each individual array. Okay, it is a list that contains 3 items. So out of these 3 items we exchange their place. First is C2, then C1, then C is 0, and we put them inside another list. Let's run it. Okay, here you can see RGB pixels. Now this is the RGB code. Now we need the classes label, and let me just paste them directly here. So these are the labels. First is background, then hat, here, gloves, sunglasses, upper cloth, dress, and it goes up to right shoe. Okay, so we're gonna get to these two things back. First is the classes and second is the RGB code. So this is one of the essential part. Like in any way, at least you need these RGB code. I think the label you can easily get them, but these sometimes these RGB code are difficult because some of the data that don't provide these RGB code. It is essential for you to extract them in any way. Okay. Otherwise, there's also other ways. If you don't have them, you can manually extract them. Okay. I'll tell you that thing in another video, but for now, let's stick to that. Let's go down. And here return two things. First is the classes, then color map. Okay, now we're going to build our dataset pipeline. Okay. First of all, we're going to write a simple function called read image. Let's do both the thing in once. Okay, first of all, let's write a simple function called read image. Just a simple function which would take X as the image. So reading image in both binary and multiclass is exactly the same. We're going to read it as RGB. X is path. Okay, so you have read the image. Then we're going to resize it. First we would give it the width, then height. Okay, so we have resized, then image normalizing the pixels by dividing them with 255 and changing their data type to float 32. I think it also written float 32 only, but let's also explicitly define them. Spelling mistake. Okay, so we're done with the image processing. So this is really simple, exactly as the binary one, but processing mask or reading mask is a bit different. It's really different, not bit different, it's really different. First we take the path. So these two things would be exactly same because masks are also now in RGB and we need to read them in RGB. Then we resize them. Now comes the essential part. And here we have the mask processing. That is why I explicitly written thing here, mask processing. Just put your all focus here. Output. This is an empty list. So first of all, what we're gonna do, we're gonna say for color each RGB code in color map. Okay. Now we're gonna use some numpy function. So let me just write the complete code here, then I explain. First we have a cmap np.all np equal. First is x, that is our mask. So just remember, we don't normalize mask like this. So don't do this in the mask, especially in multi-class. In np.equal we have x, then RGB pixel RGB code, then on last axis equals 2 minus 1. So this line is really essential. So let's start from here. Okay, so this is np equal. So here we compare, that is the x, that is our mask. It contains pixels and this is our RGB code. So we match them on the last axis and we do this for all the pixels in our mask. Okay, so this way if it matches, if the RGB code matches in any position, okay, in the mask, so it would return a true value or else it would return a false. So we're gonna have a binary map for a specific RGB code. So first one is the background. So what I'm gonna do, I'm gonna do a break here. I'm gonna show all the mask. Okay, so what I'll do, I'll just simply call this here read mask, and I'm going to give it a path, that is train one, first one. So first of all, we're going to print this CMap. Okay. Ah, one extra is there. Okay, let's go back. Okay, so if you just see here, we have some values where this array, where some values are true and some are false. Okay, so this can be indicated to true as 1 and false as 0. So this is an array of type boolean, and we can convert it to, if you say, an integer where true would be 1 and false would be 0. So let's save this. Let's call it back just cmap.png. Cmap, because this is 0 into 1, that's multiplied with 255, and I'll show you how it look. Okay, so this is the mask which we have saved. So if you see exactly from the mask, this indicate your background, because the white portion is the background. So this way we have the mask, a binary mask for the first class. Okay, for that specific RGB code. Let's now run it for all. So what are we going to say? Color I and enumerate. I'm going to show you binary mask for all. Okay, so we're going to remove the break statement from here, and we're going to rewrite the name also. Add I. So I here represent the class label, that is from 0 to 19. So this is done. So let's go from starting. So this is the map for class 0, that is background. Then this is here. Then I think this is something, I don't remember the class name, but just see, if for this class third this is black, this means that this class is not present in that image. Fourth class is also not there, fifth is there, sixth is there, seventh. So this way we have the mask for all the 20 classes. Now I hope you have clearly understood what this line exactly mean here. This is really essential and important line for the processing of multi-class mask. Those RGB masks, they are not processed like that, they take time to process. Okay, so what I'll do now, we're gonna take this output list and append that mask here. So we append all the mask inside this empty list. So we have all the masks in the sequence, and they are in a specific sequence, if you see, because we follow the sequence which is provided by this color map list. So now what are we gonna do? We're gonna say output, we're gonna stack them on the last axis, that is my -1. And then we're gonna basically, because those aren't true or false, that is boolean data type, now we're gonna convert them to integer, unsigned integer 8, and we're gonna give our value back, that is output. The mask, this is image processing code, and this is the mask processing code. I hope you just get it. So let me just simply revise it. Let's revise it again. So first we read the mask as RGB, because our masks now are in RGB. Then we resize them. Okay, then now begins our mask processing. So in mask processing, what we do, we initialize an empty list. After that, we have a for loop over all the RGB codes. So for each individual RGB code, we match it against our mask, and we do that for all the pixels. And if in any position it matches, the RGB code matches to the pixel value, then it returns a true at that place, and else it returns a false. So this way we get a binary mask, that is CMap. Then we append that CMap to this output list. Then we create a stack of that list on the last axis, and we change the data type to unsigned integer 8. So this is our mask processing. Now let's write some more code. Let's call it pre-process, not process, because this is basically some pre-process. Then here we're going to take two variable x and y. So here x and y represent the image path and the mask path. Define a function called f. Again, it takes x and y and they also represent the same thing, image path and mask. Let's decode those paths. Now here we say x, we're going to call our function read image, we're going to give it x. Y represent mask, we're going to call our function mask read mask. Then let's give those value back, x and y. Simple. So this is the function which takes the image and mask path and give you those back. Because now see, we are using multiple function which are outside the TensorFlow, that is OpenCV, NumPy and all the other things. Because those are not inside the TensorFlow, so we cannot explicitly directly use them. So we have defined this function. Now we're going to call a function called tf.numpy function. We're going to give the name of the function which you want to use, that is f. Then the input to this function x and y, and then output data type. First is float 32, second is unsigned integer, and it return two things, image and mask. Image and mask. Now we need to set the shape for this image and mask. img h, img w, and 3 because it is an RGB image. Mask dot set shape, same height and width would be there, and the number of channels in this mask would be number of classes. Then we're going to return the image and mask. Done. So this is the pre-processing code. Now we'll move on to the dataset pipeline using the tf.data API. Let me simply copy paste it because that is really easy to explain. So here the x and y represent the list of image path and the mask path, and the default batch size is 8. So first we define tf.data.dataset from tensor slices. We have this x and y. The next we shuffle the dataset. After that we use our pre-process function to read those image and mask properly. Then we arrange them in a batch. Then we call a prefetch command. Then we return the data. So this is really simple. This is not that difficult. Main understanding part is read mask and read image and this pre-process part. Now let me remove this from here. Now we'll have our dataset pipeline. So here we have defined train dataset and valid dataset, and we have called our tf underscore dataset function, which takes the image and mask path list. It is train x, train y, and the batch size would be equal to our given batch size is 16. Then valid x, valid y, and the given batch size. So this is our dataset pipeline. Now let's move on to the model part. So model would be the unit called build unit. First it would take input shape, then number of classes. Now we're going to compile our model. First would be loss. So loss is categorical cross entropy. So in case of binary segmentation, you can use binary cross entropy, but in case of multi-class segmentation, you will use categorical cross entropy. And next we're going to have our optimizer, that would be add. Okay, now let's print the summary of this model just to check that till now everything is fine or not, otherwise we would have some error or any other thing. Let's see. Okay, so we have the summary of the model. So till now it is working fine. Now we're going to move on to the training part. So first of all, let's define the callbacks. So we have 4 callbacks. Just focus here what each callback do. First is model checkpoint. So while training, we do not want wait file to save for every other epoch, because they can be case for first epoch it is improving, second it is not improving. So we want wait file only to save when our best performance is there, that is when our validation loss is reduced or it is decreased. In that case it saves your wait file, otherwise it won't. If your validation loss increases from previous epoch as compared to previous epoch, so it does not save your wait file. So this way you would get the best wait file saved. Then is reduce LR on plateau. So in when you train it over and over time, so what happen is, so model started getting saturated, the improvement is not there. So in that case it decreases your learning rate, so there would be performance improvement. On third we have the CSV logger. So while training you will have a lot of values like training loss, validation loss, and other thing, learning rate. So CSV logger callback is gonna append all the things in a CSV file. And last is early stopping. So this is our stopping mechanism. So it checks your validation loss. Let's say for continuous of 20 epoch, the validation loss does not decrease. This means no improvement is there. So it's gonna stop the training. And now comes our model.fit part. That is the last part of file. So here we give the training dataset, then validation dataset, number of epoch, and callback. And we are done. So now I'll train it and you're gonna see how much time it's gonna take, because the dataset is really huge, and in that also we have decreased dataset to up to 10,000, out of which we are using 6,000 images for training. So if you see, this take near about 4 minutes or 6 minutes, I don't know, it would take 4 minutes. So I'm gonna stop it because I've already trained this model for an, I think 15 epochs. So I'm gonna copy that thing instead of training it again. So let me just have our folder here, file. Okay, I'm not showing it to you. So we have files folder here, and I'm going to paste those. Inside our files folder, we have 2 files. First is model.h5, second data.csv. So here, if you see, we have trained it for 15 epoch, and this is our training loss, this is the learning rate, and this is the validation loss. So our validation loss is 62% and our training loss is 43%. So I'm not able to train it anymore because it's taking a lot of time and I have other works to do. But with this training also, it's gonna give you some good performances. So let me close that file. So now we are done with our training part. Let's now move on to the test part, and that is also one of the major change when you moves from binary to multi-class segmentation. So first of all, let's define all the things which we require for our testing part. So first of all, we have imported all the functions and libraries. Then at last, if you see, we have our sklearn, from where we import the accuracy score, F1, this, and other thing. Okay. And from train.py, we have also imported the load dataset, create dir, get column map. Okay. Now let's move on to the main function. And I'll copy paste a lot of thing here. Okay. Because those are exactly same to the training part. Let's go to the starting. So first we seed the environment to make sure both the test and training have same randomness. Then we create an empty directory called results. Then we set the height and width as same as defined in the training, same number of classes, then dataset path, then the model path. Okay. And here we have the get color function, which would give us the classes and the list of RGB code. Then we call our wait file, that is we load the model. So here we can say model.summary. Then we load our data set. Now let's run the test.py. So here if you see, we can, our model is loaded here. You can see the summary of the model. So this means our model is fine. And here after that you can see the split, that is training, validation and testing. So in testing we're going to use our testing set to evaluate the model. Okay, so here we're going to do two things: prediction and evaluation. Prediction and evaluation. Let me do capital it. Okay, so I'm going to do it sequentially and I'm going to explain each of the things here. First of all, for x comma y in TQDM. So TQDM is a progress bar. Then zip. Here we have test x and test y. So when you have more than two lists and you wanna loop over them, so you're gonna use zip, specify both of them inside, and have an individual variable representing each of the list item. Total is equals to length of test x. So this total is required by TQDM, so it specifies how many iteration this loop would run up to. So let me just print both x and y. So these would basically the path. Still, let's print them. Okay, so you can see this is the image path, that is 4097. This is the mask path, same 4097. So we need to extract this name, that is 4097, okay, from an image or mask path, does not matter, because we need to save the images. Just give a bit focus here. So what are we going to say? X dot split. And if we see both image and mask path, I'm using an Ubuntu system. Let me just show you my settings. I'm using an Ubuntu. If you see, where is the version? This 22.04. Okay, maybe you are using Windows or Mac. This path can be a bit different. So what my logic here is, try to understand the logic. That we have this path, and we remember the name would always be in the end, and all the text are separated by this slash, which separate your the directories, files, etc. So we're gonna split this string based on this slash. Now let's print the name. The name would basically be a list of different items. You can see it's a list, and in this list our name with extension is in the last. Let's do -1, that is the indexing. So you can see the name with extension, but we only need name. I'm gonna say dot, and again we split this name on the base of this dot. Again a list. First we have the name, then extension. So here we're gonna say 0, and we have the name of the file. So we're gonna use this exactly same name when we save the predicted mask along with the input image and the ground truth. First of all, we're gonna read the image. Okay, so I'm gonna copy paste this code here. Okay, so first of all, we read the image using OpenCV, and we read it as an RGB. Then we resize the image, and we save this image in another variable called image_x. We're gonna need it later on. Then we normalize the image and add it the dimension of the first axis, because this is only one image and model take images in form of batches. So here this image would be a batch of 1. Now we're going to read the image. I will remember the process of reading the So this is our mask. We also read it as RGB. We resize it. Then we save this mask in another variable called mask underscore x. Then we have this variable or empty list one hot mask. And again we do the same process that we do in the training part in read mask. Yeah, we do exactly same thing. We can also call these function, but it's up to you. You can call them and your code would be a bit smaller. Then till stack it is fine, okay, but after that it's change. But here on this we apply in argmax. Okay, so what happened in argmax? Let's say you have a list, let's say simple vector. Okay, a vector where you have random values. So what argmax does, it give you the index of from the vector which have maximum value. So let's say on index 5 you have maximum value of 0.9, so it would give you an index number of that specific value 0.5, 0.9 maximum value that we do here. Then we changes integer, changes to integer 32. So this mask underscore x is our RGB mask, and this one hot mask is basically our normalized mask. Here it would have pixel in the range of 0 to 90. So I'll just show you that. Okay, so we'll save both these mask x and one hot mask. First I'll save the RGB mask. I'm going to say RGB mask dot png mask underscore x. Okay, again some error, some indentation error on reading the image, line number 54. Oh, I get it. This is where I have the error. Okay, let's again. Okay, it stops, so it saves your RGB mask. So this is your RGB mask. It really it look nice, exactly same as it should be. Now next we're going to save our one hot mask. So the pixel range would be from 0 to 19, so it would not be easily visible to your eyes, but still we're gonna save it. Okay, so it is also done. Now this is your normalized mask. Okay, here I hope you can, if I zoom it, you can easily see these different shade of darks, the gray, the shade of gray. Now these are in the range of 0 to 19. You can even see them. Okay, this is one way. Just multiply them with just one. There's a unit, that is 255 is the amount of total number of pixels. Divide them with number of classes. Okay, and save them and run it again. This way you can easily see them in grayscale format. Now you can see them in the grayscale form, but RGB looks much better. So I hope you understand how the normalization part occur. Okay. So we have read the image, read the mask. Now we're gonna make predictions. So we have our model dot predict. We give it image. We say verbose to 0. We don't want any information while predicting. How much time it take? None of that. So because image is in the is a batch, is in the batch, and batch only contain one image, it would also predict a mask in batches, and input has only one image in batch, so mask would also have one image in a batch. So we index it at position 0. Then the prediction. Now I'll put some values here. Print pred dot shape. Okay, now just see the shape of this prediction and see the shape of the after argmax. So you see height and width remain the same, the number of channel differ. In while prediction it has 20 classes. Okay, For each class it has a separate value, but after we apply argmax, it has only one channel. Okay, here it has only one channel, but in that one channel it has values 0 1 2 3 4 till 19. For each, what we say, for each pixel in this mask, prediction mask, it has one class. So each of those 20 classes, from each of those 20 classes it has one class. Now let's save that also and see how the prediction mask look. So we're going to say pred.png. Pred. It also have a range of 0 to 19. We cannot see them. Again, we're going to say 255 divided by 20. That is number of classes. If a class is more than 255, then I don't know how we can log it. Okay, so this is done. Here you can see the prediction. The prediction is not that good and not that bad, so it's an optimum value because we haven't trained the model, and we also have decreased the number of training samples, and we're also using some simple model like UNET for 20 class. So I believe the prediction is really well. Now if you see, the prediction is in grayscale format. Now how are you gonna compare it with the RGB one? So now we'll learn how to convert it to RGB. There's also a way to convert it to RGB. Now what we do, we're going to save the prediction. So let's define the path where we're going to save the image. Save image path. Okay. First would be name of the folder which we have created initially. We remember this result folder. Inside that result folder, we're going to have the name of the file. We have extracted the name here. Name, then extension, that will be .png. Then we have a function called save results. We're going to build this function is going to take image, then mask x, then prediction, finally save image path. It's going to take all these things, and we're going to create a function, go back to the top. Okay, so what are we going to do? We're going to concatenate 3 images at once: input image, ground truth mask, and the prediction. So we need to make sure, first of all these have same height and width, and especially number of channels should be same, because height and width would be exactly same all third, but number of channel would be different. So we need to make sure that all of them have. So first of all, we're going to print their shapes. Then pred dot shape. If you see, first input image and the ground truth masks have same number of height, width, and number of channels, but for this prediction we have one channel only. Okay, because if the channel is not defined, this is by default assume it is only one channel. Okay, we need to now convert this normalize, or you can say the grayscale image, to RGB. So let's now, so before that, remember, while you save image, we're going to separate image and mask with a small white image. So let's build that. So we're going to say height by width image x dot shape line, that is separating image mask, image and mask, and mask and prediction, and p dot ones height, width would be 10, and number of channel would be same as the rest. Okay, for the prediction, let's now increase its dimension. So if you remember, it has just height and width. Let's increase its dimension on the last axis. Now I'll print its shape. Now you can see we have increased its dimension on the last axis. Now you cannot say we have written -1 here, so this is 1 here. Okay, so -1 here indicate the last axis. Okay, now let's build another function to convert it from gray scale to RGB. Now give focus here. We're gonna take classes. Just we assume it's gonna take classes, then the list of RGB codes. Okay, let's now define this function again. We take classes and the color map. So first of all, let's save the height and width from the prediction because we're gonna require them. Then we're gonna change the mask to integer 32. Okay, now then we have empty list output, and this output would save all our RGB pixels. So we're gonna convert from the grayscale pixel to RGB. So let's do one thing. We're gonna say for I pixel in enumerate mask dot flatten. So what have we done here? Okay, in this complete line, this is really essential. Let's focus it. Because for binary segmentation we don't need this part, but for multiclass we need this. So what have we done? We have flattened those pixels, okay, into a one dimension. So now this would be long vector. So now on this long vector it would be a list of values. Okay, so let me just give an idea how this would look. So let me run it and show you how it would look. Okay, there's some error. Okay, it's prediction, not mask. I'm just a bit confused. It's also mask. Again, same error because I'm just assuming it mask instead of prediction. So this is change in variable name. The logic is I'm going right. Okay, here you can see simple list. Okay, you can see from this, you can see its size. It's the simple list. So what have we done here? We are looping over this simple list. So each item in this list is a label from 0 to 19. So what are we going to do? We're going to say output dot append. So we're also going to create a simple list like this only, but in that instead of the grayscale pixel value we have RGB pixel value. So we're going to call our color map and we're going to say pixel here. So we're going to do indexing. So let's say for background, in this prediction for background the pixel would be 0. So if we go to our color map, go back on the 0th index in the class, it would give you the name of the class, and in this color map it would give you the RGB code because we have saved them in a specific sequence. Now we have our RGB code in this output. So when the loop is complete we would have all RGB. So we can simply resize it, not resize, reshape it. So we can say height by width by 3 and we're gonna get that value back. In this way we convert it from grayscale to RGB mask, and this is one of the important thing when you move from binary to multi-class segmentation. Okay, so let's move to our save results. So let's now print the shape of the spread and see if we have any error or anything, because there can be multiple error while doing. Okay, now you can see it also has number of channel as 3. Now because all the 3 image, mask and the prediction have same height, width and channel, we can easily concatenate them. Cat images np dot concatenate. Oh, this should be small. Now we're gonna give it a list of images or arrays. Image x, then line, then mask x, then a line, then pred, and after that we're gonna give axis 1, and we're gonna save the image. Or this should be cv2.imwrite. That is the command for writing the image. Save image path cat images. So this is the process to save your image ground truth and prediction for better comparison. So let's do it, and we're gonna do it only for one image. So it is done. Now let's go to our folder results, and here you can see we have one image. Now this is your image what we have saved, the concatenated image. First we have the input image, second we have the ground truth, and third we have the prediction. So if we compare and see the ground truth, not the ground truth, the prediction, we have our prediction in RGB. That is one of the fantastic thing. So first of all, don't give focus on the performance. Just see if you have that exact result which you want. Later on, you can improve the performance. The first thing is it should run in a good way. Performance matter the last, matter the next. First, it should run. Okay. And if you compare the performances, that is not good and not even that bad also. Because if you see the ground, there are 2 people, but in image there are multiple people. But our prediction has 3 human being indicated. So this is one of the best thing. But that is one of the drawback here is that because we have 20 classes here, so our model get confused which one is what, which one is what. So because this is only one image, we cannot judge entire model on one image. So let's now work on the evaluation part. So we're gonna calculate the matrix, that is f1 and Jaccard. Basically 2 we're gonna work upon. So first of all, we're gonna flatten the array for both the prediction and the one hot mask. Next we have our labels. These are from 0 to 19. Now we're going to calculate the matrix. For that we're going to use our what library, I don't remember, the sklearn. So I'm only using f1 score and Jaccard. For the rest you can calculate them accordingly. After this video is done, you can understand how. So first is f1 value. For that we use f1 score, we give it one hot mask prediction, and we give it the list of labels we have. So make sure both one hot mask and prediction are integers. That would work best here. Then list of labels, that is from 0 to 19. Then average none and 0 division none. And same thing we have for the Jaccard score. Now next what we're gonna do, we're gonna say score dot append f1 score, not f1 score, f1 value, then Jack value, that is Jaccard value. So because we need to, now we're going to calculate mean for all. Okay, so first of all, let's do one thing. I'm going to print f1 Jaccard for this single image, because this f1 and Jaccard is not for one class, it's for 20 classes. Just see. So we're going to have a list with 20 different values, and each representing an f1 for different class. Again, I'm spelling mistake. Like when you code for long, I'm like coding for more than 1.5 hour, and I'm reached at that point that I now have confusions. Okay, see, a lot of confusion. I'm sorry for that. Okay, let's now take a deep breath and again continue working with our full concentration. So I want you that you'll at least subscribe my channel, like this video for this hard work I'm doing for about like 1.5 hour. At least just support me in this way. So now you can see the 20 values, and each value is representing f1 for each class. First is background, it's 94, it's really high. For some classes it's low, like 0.2, some classes it's even 0. So that's okay, because here we are implementing it, we are not focusing on the performance. Our main task is at least we have some baseline. Okay, for performance we can increase the data set, we can increase the number of training epoch, we can change the architecture, we can add some attention mechanism, we can use transfer learning. That means we can replace the encoder with a pre-trained network like ResNet 50, DenseNet, any other pre-trained network. So that would give you performance improvement. So here we have appended the value in the score variable. So once I'm going to do one thing, I'm going to shorten the amount of test sample so that it runs fast, because if I wait for, let's say, whole the 200, it's going to take a bit of time. So for working, we're going to have 10 samples. So let's go to the end. Let's remove this break. So we're going to go now outside the loop. Okay, so this is the loop we are working on. So we're going to go outside the loop because we have our score, our f1 and Jaccard in the score variable. Now let's say call some matrices values. So we'll convert it to an array first. Oh. So we have converted to array. So we're going to print its shape first. Because for now we have 10 samples, okay, in testing. So if you see, the shape is 10 by 2 by 20. So here 10 represent the number of test sample, 2 represent number of matrices, we have 2 matrices f1 and Jaccard, and 20 represent number of classes. So first of all, what we need to do, we need to have a mean score on those 10 samples. So let's say score equals to np.mean. Okay, because we want mean for all classes. Okay, not mean of all classes, but for on the whole image, mean of all the predictions. Okay, so for that we're going to say np mean, then score, and we're going to say x is equals to 0. Now let's run it again. Now see the difference in the shape. Here you can see the shape is 2 by 20. So 2 represent number of matrices and 20 number of classes. Now here we're going to open a CSV file in which we're going to save our scores. So our CSV file lies in the files folder and its name is score.csv. And inside it, we're going to write first class, then f1, then Jaccard. So these are the textual information we have written. And some more lines of code here. So L is some list. So it represents, first we have class, then f1, then Jaccard. So this is a sequence in which we're going to print. For each class, we're going to print f1 and Jaccard. So for now, we're going to loop over the number of classes, that is this 20. Okay, for I in range score dot shape, that is 1. So first of all, let's extract the class name. What is the class name? We're gonna extract it from classes, that is I, because it is 20 and we have 20 classes, so this would run up to 20. Okay, So this index, there would be no index out of error with this. Then we're gonna have our f1. We're gonna say score. F1 lies on 0th index for this specific I class. Then jack score index 1 for I class. Then we're gonna print it on the screen and also write back to our file. Let's now do f.close. Let's close our file. So let's print the score on the screen and see if there's any error or any other thing. Okay, you see a good amount of thing we have in a proper way. So first we have class f1 and jackcard, and for each class, that is background, we have 86% f1, 77% jackcard. For head we have 24% f1, 21% jack. So like this we have calculated score for each class. Okay, now at the end we also want to do one more thing, that is a mean of all those class. Okay, a mean f1 and a mean jackcard for all the combine. If we combine all the 20 classes into one single value, that would be a mean. Let's do that now, because we can easily compare those, but we also need a mean value for better comparison. So let's print a line like this. So this is one line, and we're gonna have one more line after that score. After that, what we're gonna do, we're gonna have a class mean. Let's say class mean. If I go back to this shape, if you remember this shape, so we need a mean over all the 20 classes. So we're gonna find a mean on the last axis. Okay, np dot mean, that is score axis is -1. Okay, now here class name is mean, or f1 equals to class mean 0 position, jackcard would be class mean on index position 1, and we're going to do the same thing. We're going to print it and write back to the file. I hope you understand why I'm writing all these things. Yeah, I'm writing just these things so that it displays in a proper order, because looks are also important. Looks makes you feel that it's really good. Like if I don't display those things in proper order, you're not gonna like that much. Here you can see we also have this mean score, and it looks really nice. And we are also saving these thing in a text, in a CSV file. In the files folder, you can see we have this score file. Let's open that. So here you can see we are saving all these value in a CSV file, so that later on you don't need to run the entire thing again and again. Okay, you will just go to this CSV file and you have all the score. So for these 10 samples, we have a mean f1 of 21% and a mean jackcard of 17. And now we'll say these score are really low, but just see that it has 20 classes and we are using a simple architecture like UNET, and that too we are training it on just 15 epochs. So this is the reason, like if you have less classes, you're gonna have better performances. The more the class, the more it is like difficult for the simple model like UNET to focus. Okay, so I hope like this entire tutorial, this long tutorial on multi-class segmentation would help you. And if you really enjoyed this long video, just make sure that you like this video, share it with your friends, share it in Facebook group, WhatsApp group. Just share this information, it would be helpful for me. And in the end, just make sure that you subscribe the channel, and also hit that bell icon, and you can also join the membership. Give me special thanks just for your support. These things like help as a creator, because we spend our time here. At the end, I want to say thank you. If you have any query, just write it down.